Hello. So what we're going to do today is we're going to start module 4, which is talking about structures of organic compounds. And part of this is in chapter 3. So what we're going to do, we're going to start with conformers. What are conformers? So in organic chemistry, the structure of compound is very important in terms of predicting the outcome of a reaction. So we need to understand how compounds look like in a 3D setting and see how we can make them react based on their structure. So what are, first of all, conformers? Conformers are the same compound. So the same compound that has different spatial arrangement. So it's the same compound, but different spatial arrangement. So what does that mean? A same compound with different spatial arrangement. Let's look at ethane. So ethane is CH2CH3. So the way we can represent it is a perspective representation. We know that ethane has CH2CH3, which means each carbon is an sp3. So we learned in general chemistry that each carbon is a tetrahedral. So this is how ethane would look like in a 3D representation. This is called perspective. So this kind of representation here is perspective, which is the best way to represent it as a 3D on a 2D space. So what is a perspective? What do these mean? These two hydrogens are outside the page, in front of the page, so above the page. These two hydrogens with dashed lines are underneath the page, behind the page. And these three bonds are on the same plane as the page. So whenever you represent something in perspective, you have to represent a carbon with wedges and dashed lines. The wedges means the bonds are coming out of your paper, and the dash means behind the paper. Now, this is a good representation, but it's not enough to explain conformers. So how do we explain conformers? We're going to pretend I'm looking on this direction. So this is my eye, let's say, and I'm looking this way. So basically, I'm looking on the side of the molecule to this carbon. So if I'm looking from the side, the carbon will be right in front of me, and above it, there's a hydrogen. And this one, since it's behind the page, would be to the left, and this one would be to the right. So we can represent this carbon as a dot. And then above, there is an H right here. And to the left, there is a hydrogen. And to the right, there's a hydrogen. So if I circle them in colors, so this would be the pink because it would be to the left. This would be the green. And this is the top hydrogen right there. So this is how I would see it. I would see a carbon, which is the dot that I represent here. And above the carbon, a hydrogen, and then the other two hydrogens. But also what we see is we won't see this bond because it's going to be hidden, but we have a carbon right behind it. So how do we differentiate from this carbon to this one? This, I put a dot for it. This one, we put a circle. So the circle means it's a carbon behind the front carbon. Now, what is attached to this carbon? You see that there is this hydrogen right there that is right behind this one. So in the back, I'm going to have an H, but that's the purple one. So they're behind each other. The orange and the purple are behind each other. Then behind the green, with this one, there's this one. So I'm going to put it here. So the one on the wedges, they're both behind each other. And then the pink here is behind this one. So this representation is called perspective. This representation is called Newman projection. So a Newman projection is the carbons are represented with dot and a circle. The front carbon is always a dot. The back carbon is always a circle. And notice what I did here. The bonds attached to the back carbon come out of the circle, not from the dot, meaning that these are attached to the back carbon. So all these bonds, you have to make sure to show that they're attached to the back carbon, not the front one. So what happens? Why do we represent it with a Newman projection? We said here, I didn't finish my definition, we said same compound but different spatial arrangement. But why is it different spatial arrangement? It's due to a CC rotation. So what does that mean? This CC bond, all single bonds, you should know, all single bonds rotate. So when they rotate means like they're spinning around. So when this rotates, you can see that these hydrogens will move. So let's pretend we rotate this a little bit. So if I rotate it this way, you don't have to rotate both. So let's say one stays fixed and the back one is rotating. So I'm going to show you the different possibilities here. So I'm going to restart with this representation. And I'm going to pick two of them. So let's say the green, I'm going to keep it green so you can follow what happened behind the scene there. And let's say, so here, the back has an H, and then another H here, and then another H here. So let's pick this one in red. So this hydrogen in red, and this hydrogen in green. Randomly, I just picked two to kind of follow them. So if I have a 60-degree rotation, I'm going to make this move a little bit to 60 degrees. So what's going to happen is the front one is still the same. I'm not moving the front carbon. I'm just moving the back one. So this green H is still in the same place. But behind it, the red hydrogen now is at a 60-degree angle. That's where my red hydrogen is. And then I have this and this. Now, if I keep rotating again 60 degrees, the front is still going to be the same, H, H, and here we have that green hydrogen. And in the back, the red hydrogen now is here. And then there's one here and one here. So you start to see that these two are the same and this one is slightly different. So if we rotate again 60 degrees, we're going to get this. So the H stays the same, and the back one, the front hydrogen should be green, but then the back one is now down here, the red one. So all of these are considered conformers. What happened is we have the same molecule, but the only difference is what happened as a result of a rotation around the CC bond, so around the CC bond. Now it is obvious that these two hydrogens are back behind each other. They're hiding each other. So this position is called eclipsed. This one, they're far from each other. So this is called staggered. This is an eclipsed. This is a staggered. So what happened constantly, without even us controlling it, this molecule will constantly go from an eclipse to staggered, to an eclipse to staggered, to an eclipse to a staggered. And in between, you see that these two hydrogens are behind each other, eclipsing each other. That's the reason it's called eclipsed. And here they're far from each other. So it is clearer that this structure, the staggered ones, are more stable because the atoms are not into each other's path. They're not too close to each other. These staggered positions have atoms that are as far as possible from each other. So these are the most stable. So every staggered position is very stable. Every eclipsed is less stable. So what you have here, we can represent it in a diagram, what we call the potential energy diagram. So if I call this as my molecule A, I start with this. A is an eclipse, which means it has low energy. It has high energy. It's not stable, meaning, you know, there's a lot of interaction between the molecules. 60 degrees later, it will become a staggered position. So that's more stable. Then you rotate it another 60 degrees, it becomes eclipsed again. So this would be 120. Then 60 degrees later, which is 180, more stable, then up, and then down. So you get this idea that the molecule keeps on going back and forth from a stable to an unstable, from stable to unstable, stable to unstable. And a good diagram is given in your textbook, so you can check it out on page 119. So just check page 119 for a complete diagram that shows what are the conformers and how they're different and how they're similar. So in terms of bonding, they're exactly the same, but in terms of position and spatial arrangement, they're very different because the staggered are very stable and the eclipsed are not that stable. So this is a very simple molecule, but what if we come up with a different molecule? So let's say, instead of working with ethane, I'm working with a substituted ethane. So let's say, not substituted, let's say butane. So what is butane? It's CH3, CH2, CH2, CH3. So this is butane. I'm going to focus on the middle carbons right there. So, and I'm going to make a perspective representation of the middle carbons. So if I'm going to call this one carbon 1, carbon 2, I'm going to put the carbon 1 in the front and carbon 2. I'm going to just do the perspective first. So carbon 1 is right here, and it has 2 hydrogens and a methyl. So what I can do is put the methyl here, and then put a hydrogen in the dashed and 1 in the wedge. So this is one of the carbon, which is C1. C2 would be the same. So we have a CH3. See how C2 is attached to CH3. And we have an H, and we have another H. So this is, I shouldn't call it C2, 2. This is 1, 2, 3. So I'm focusing, this is carbon 2, carbon 3. So I'm focusing on this carbon 2, carbon 3, where we have the substituent. So what would be the Newman projection? So this is, remember, this is a perspective. which shows each carbon as tetrahedral. Now, if we look here, so this is supposed to be the eye, and that's the angle. We're looking through C2, C3. So C2 would be in the front, C3 in the back. So the front carbon would be a dot. And then on the top, there's a CH3. And then to the left, there's this H, which is, I'm going to put it like this. And then the other wedged H. I put the dash on purpose to just kind of show you, it's not really dashed now because I'm looking at in the front. So all these three are in the same plane in front of me. Now, behind the C2, there's a C3. So I put a circle. Remember, the one in front of you, you put a dot. The one behind, you put a circle. And what's attached to the circle, you have a CH3 just behind the other CH3. And then you have an H. And then you have an H. So this is the perspective. This is the Newman projection. Now let's try to start again with that Newman and keep rotating and see what happened, okay? So if I take my Newman projection again, I'm going to represent it here, and I'm going to put the CH3 one, I'm going to circle it with pink, the front one. And behind that front CH3, there's another CH3. And then I have H, 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 H. So this is definitely an eclipse, and you can see that this CH3 is right behind this one. And they're kind of like almost touching because they're right behind each other. It's too crowded there. So in organic chemistry, when something is too crowded, we call it steric hindrance. It's hindered, it's like pushing each other, these two. Now, 60 degrees later, what do we get? We keep the front one like we did earlier, CH3, HH. We're going to keep consistent with the front one, but the back one now is here. It's staggered. So this is our green CH3 that moved 60 degrees down. Now we go another 60 degrees and we get this. So now the CH3 is here behind the H. And the front one is still a CH3. And we have an H, H, and H. 60 degrees later, we get, so I'm going to keep focusing on the pink is still in the same position, and the green is the one rotating. 60 degrees later, we get this. So the front is still CH3, H, and H. And in the back, the CH3 is now down here, and then H, H. So the front is still the same position, and the green keeps rotating. Now I rotate 60 degrees later. What do I get? I get this. So the front is still the same, but then the back, the CH3 is now in this position, and it's an eclipsed. Now another 60 degrees later, we get an eclipsed, a staggered one. So CH3 is here. So this is the green one, moved over there. The front one is still here. And then 60 degrees later, you get back to that original structure where the two CH3s are behind each other. So, what can we say about all of these? It is obvious that all the eclipsed, the staggered here, are more stable because the methyl groups are far from each other. So this and this, they're about the same distance here and here. So these have the same stability, the same level of stability. These are eclipsed, they're not, so This is worse than this, although they're eclipsed. So this one is eclipsed by an H. This one is eclipsed by an H, whereas here, the two CH3s are eclipsing each other. So this is not stable at all. Same here, this and this are the same, and this are the same. So the least stable of them all are these. Then we have these two because they're still eclipsed. Now, what do we call these two? See where the CH3s are slightly, they're 60 degrees off from each other. These are less stable than this because the CH3s are completely opposite from each other. So this position is called anti. This is the most stable. These are called gauche. So this is a gauche. So what does it show then? In the end, the summary is that we go from a very unstable eclipsed to a gauche, which is staggered, to another eclipsed that doesn't have a name, to an anti, which is the most stable, then an eclipsed, then a gauche, then an eclipsed. So your diagram here will be different from the previous scenario. The least stable is this situation. So I'm gonna just label them. I'm gonna call this A, this is B, this is C, D, E, F, and G. And each one of them is a 60 degree apart from the other. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So each time I do 60 degrees. So from here to here, we have a gauche, which is stable, but not as stable as this one. So I have the gauche right here. And also then an eclipsed, which is really unstable, but it's better than what I started with. Then we have, this is the anti, which is the most stable of them all. Then the eclipsed, which is this one, the stable one, kind of more stable than the original one. Then another gauche, and then go back to the original one. So your diagram here will look slightly different than the previous scenario. And you have a clear explanation and similar thing on page 121. So this would be page 121. So this is a little introduction about conformers that are same compound, but different stability, different structures because of the position of their substituent. So the gauche is when the two substituents are 60 degrees apart from each other, and it's in staggered position. And anti is the most stable because the two methyl groups are far from each other, so they have the less steric hindrance. They're really free here. And of course, the molecule is going to constantly go through all of these phases, up and down, up and down. And that will, of course, create some kind of specific properties. And by the way, although we know that these exist, we can also slow down the rotation by observing them at very, very low temperature. That's how we know that they do exist, all of these forms. And these would be the gauche, the gauche. This is the anti. We can observe them, but we cannot separate them. So these are structures that you can observe with some kind of techniques, but you can't physically separate them because they all have the same melting point and boiling point. Now, let's go to the next type of conformers, which are cyclohexane. Of course, there are other type of cyclic compounds that have conformers, but we're going to look at the conformers of cyclohexane. So cyclohexane is a molecule with 6 carbons, and it's cyclic, it's a ring. This is a very simple representation of cyclohexane, but it doesn't really show the substituents or the atoms where they are in a 3D environment. So how do we represent a cyclohexane in a perspective form? So this explanation, by the way, is written in detail on page 125. It starts at page 125. So what do? You see these two bonds right here, they're parallel to each other. So what you do is you create two lines that are parallel, more or less. You start with these two. So this and this are these two. Then you create here something like this. And then you have the same thing on the other side. So this is a real cyclohexane. This is more of a 2D. This is closer to what a 3D would look like. Now I want you to notice something. This one is parallel to this. Okay. Also, this one is parallel to this. So every two lines in a cyclohexane are parallel to each other. So automatically, this one is parallel to this. So each two are parallel to each other. But that only shows two bonds per carbon. We're missing two more bonds. So where are the other two more bonds? You have one bond that's up. So you see when this carbon is upward, there's a bond that goes upward. This carbon is going down. You see how the two bonds are leaning to the bottom. So you have a down bond. Same thing here, this should go down. This is pointing up. So we have an up bond like this, which is completely, they're all parallel to each other. This one is also up because the carbon is pointing up. It's pointing down, so you have it down. So all these black bonds that are represented are called axial. So they're all parallel to each other in an axial way. So it's like a z-axis or any kind of axis you can think of. But we also have, so these are just parallel to all, they're all parallel to each other. You have three upward and three down. And what we have left is the fourth bond. So how does it work, that fourth bond? And this is what's interesting is, see this pink? This is parallel to the pink. So this and this are parallel to each other. Now in here, the one here is parallel to this. So, which is parallel to this. So these two, so you see 1, 2 carbon, so this and this are parallel. This and this are parallel. So you look at the carbon next to it and create what's missing, that parallel bond. Now in here, see, we have to have an equatorial. So by the way, these are called equatorial. They're all called equatorial. They're coming outside of the ring. Now, we have this one is going down, so it's, the other one would be parallel to this. Okay, this one is up, so the other one will be parallel to this. So these two are parallel to the blue. And then we have this one, so you see the pink, so this has to be parallel to the pink. And finally, this one, we have a purple here. It has to be parallel to that purple. So this is a real cyclohexane. And it looks like a chair, so this is called the chair form of cyclohexane. So cyclohexane, in a simple way, we represent it like this, but in reality, it should look like this. So this is the perspective of a cyclohexane. It has the ring that looks like a chair, and then you have the other bonds that are either axial or equatorial. And you notice all the equatorials are outside, away from the ring, and the axial are either above the ring or below the ring. So it's obvious that because they're above and below, they will have more interactions, and they're not the most stable ones. Now, what if we want to do the Newman projection for this, just like we did earlier for the ethane? What we need to see is, imagine your eye is looking in this direction. So these 4 carbons, 1, 2, 3, 4, these 4 carbons are all in the same plane. See, you can draw a plane right there. And when you look from here, you see this carbon in front of you and also this one. So you have 2 carbons in front of you and also this one. These 2 are at the same level. This one is at the bottom. So in front of you, you see 3 carbons. 1, 2, 3. So this one right there to the left is this. This one is at the bottom, and this one is up. Now, if we look at them, this left one, the one I represented here, it has above it an axial position. That's this bond. This is this. Then this equatorial is away, so it's on this side. That's your equatorial. That's the one. Then this to the right, it has also an axial carbon right there, and it has an equatorial. This blue one is coming out here. And finally, the bottom carbon, it has something coming at the bottom down here and something upward, so we can represent it kind of here. Okay, this pink thing is right there. So now I'm done with these 3 carbons. 1, 2, 3. So if I call this carbon number 1, number 2, number 3, 1, 2, 3. So what's behind 1? Behind 1, there's a carbon there, so we put a circle. Behind number 3, there is a carbon there, so we put a circle. And then, see the number 2 is down, going downward, but between these 2 carbons, there's a carbon upward, so I have to connect them with a carbon that's up here. So if I want to number them, this is number 1, number 2, number 3. There are the front ones. That's the 1, 2, 3. And behind the ones, if I keep on numbering, that's 4, 5, 6. Behind the 3, there is the 4. So this is the 3, the front one. The back is the 4. And then attached to the 4 is the 5. And the 5 is attached to the 6, which is this one. And the 6 is attached to the one which is in the front. So this is how you go from the perspective to the Newman projection. Now, I'm still missing bonds here. On the 4, that's the 4. Remember, it's a circle. The 4 is attached to the 5. That's what we did. But then the 4 has an axial, a bond going down. And then it has something coming outward to the left, to the right. So that's this purple is this one. Now, on the 5, you have an axial which is going up. And then you have this one, which is here. The pink one is this. And then on the number 6, you have an axial, and you have that blue one, which is coming this way. So this is the perspective projection of a chair of a cyclohexane, and this is the Newman projection. Now, it might look overwhelming, but it's very easy to represent these because I'll show you a very short cut. But I want to explain also something else. When you see this chair position, all the bonds are staggered. They're not behind each other. They're not touching each other. So this is a very stable structure. A chair is very stable because all the bonds are staggered, just like we showed it earlier. So if it's staggered, it means you don't have a lot of steric hindrance. So now let's pretend, let's say we're going to put some substituent here. So here's a cyclohexane, and I'm going to put, let's say, a methyl here and a methyl here. Okay, I'm just picking one, but we can do so many of them. And by the way, you have so many answers, so many scenarios, and you have them in the answer keys. So how do we represent this in a chair? So we're going to do it again. We have two parallel bonds. You always start with the middle. Then you have something like this, and then you have something like this. So in the end, this should be parallel to this. This should be parallel to this, and this should be parallel to this. Then, so I just represented the ring. So that's how the ring looks like. Then I can call this my carbon 1, 2, 3. So this is 1, 2, 3. So I have, you see, this has limitation because it's not telling me where are the CH3s. Are they in the axial or equatorial? So I can pick one scenario where I put this CH3 up here, okay? And I can put the other CH3, so we have up, down, up. I can put both of them upward. And then the rest is just hydrogens, okay? So I'm going to have H's, H, 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 H and H, and here we have an H. Now, if we look again through the perspective, the Newman projection, I have this carbon right there, this one in front of me, attached to this one in front of, I'm sorry, this is also at the same level, but it's attached to one at the bottom. So we have these. You start to see that this hydrogen is away, and this one is also away. So the way to represent a Newman projection is to write the letter M. See, that's your letter M. This is my carbon right there. This is this. This one here, the bottom one, is this. And the one that's here is the right one. And you see that both of these have a hydrogen that's away. So that's what I put here and here. So these are my H's. Okay. Now, what else do I have on the right one that I represented here? We have a CH3. So that's this carbon with a CH3. Now, what do we have behind them? So behind them, we have a CH3, but they're like going to be upward. So you see here, I wrote this M letter. See how the M letter here? It's what I wrote here. But then in the back, I have an inversed M on the circle. So I have to represent a circle here, which are the back carbons. And then I have this, this, and this. Sorry, it's not ideal, but you got the idea. So you have an inversed M. You write an M at the beginning, and then you put the other inversed M, and then you have to complete with the other bond. But let's first, wait a minute, here. Behind this carbon, we have this one, so that's my number 2 here, and it only has H and H. So the back carbon has H and H. This one has a CH3 above, on top, and it has an H here. So you can write it right here. This one has an H and an H. And this one must have an H. And now you have all your bonds. Actually, I forgot to put this H and H. So you notice that the two CH3s here, they're on the same side of the molecule. They're upward. So this is a cis. The way I wrote them this doesn't tell me if it's cis and trans, but the way I wrote them is they're both axial position, they're both cis. So there are many ways we can write these structures. We could also write it this way. So I'm going to redo the whole thing. So I can leave one as axial, but this one, instead of making it axial, I'm going to put it in an equatorial position. So it's still the same molecule. In here, they're both axial. In here, I put one axial, one equatorial. And I want to represent them in a Newman projection. So again, this is this carbon, this is this carbon, and in between them is a carbon at the bottom. So I'm writing my M. Now I have an H here, but in this case, I have a CH3 on the other side. So you see the CH3 here is outside. So that's your M. And then in the back, we have an inverse M that is connected to the top carbon. Now that top carbon here, it has a CH3 and it has an H. This one, the front one, has an H and an H. And then we just have to put H here and H here. And of course, I'm missing a hydrogen on top and another hydrogen. So you see in this position, compared to the plane of this molecule where I was looking, there's a CH3 on top and there's a CH3 at the bottom. And you can see them very well in here. So if this is your plane of the molecule, on the top you have a CH3 and at the bottom a CH3. Whereas here, if this is the plane of the molecule, they're both on the same side. So that's why this is cis and this is trans. So this is the trans. So as you can see, a Newman projection is more efficient at explaining where the atoms are, and it just gives you a better idea of the different conformers. Now, in this particular case, they're not real conformers because we don't go from this to this by simple rotation. You have to literally break this bond and attach it here to create this. So these are not conformers, they're more of isomers. But what are then the conformers of this? One thing that's very interesting, and you can see it on page, so just to direct you because I don't have a 3D way of explaining it, is you can see it on page 126. So there is what we call a ring flip. So I'll show you slightly like what it means. So if I have a cyclohexane like this, what you can do is rotate this down and this up. So what happened is this now becomes the one pointing down and this one pointing up. So you can end up with this. Sorry, it's not perfect, but see this carbon right here? This one is this. And then this one is this. So if I put a substituent here, let's say I put a CH3 here, when you flip it, it becomes equatorial. So the axial becomes equatorial. And if I had here, let's say, a substituent in, let's say it was in the equatorial position. So when you flip it, it now is in the axial. So these, they keep on going back and forth. This is what we call a ring flip. So these two are conformers. What it means is like if I call this carbon 1, this is my carbon 1. The equatorial position of the carbon, right there, sorry about this, the equatorial becomes axial. And on this side, the axial becomes equatorial. So these are conformers, which means that a ring can be represented this way or that way, and you can constantly flip it back and forth. And every time you can flip it, these are two considered conformers. So this is the axial becomes equatorial and the equatorial becomes axial. And these are pretty much the different way to look at a cyclohexane as a perspective position and in terms of conformers. So why is this important? It just, you need to understand the stability of these conformers when you represent them. So let's say also, like, you need to also understand if they're cis or trans. So let's try some examples very quickly. Here I have a Br here and a Cl here. We don't represent all the atoms, the hydrogens, but you understand that there are H's everywhere. So let's look here. This chlorine is not in a position that's axial, so this is an equatorial. And this bromine is also in an equatorial. So the question here is this cis or trans? If you look closely, both of them are going downward. It's hard to read it here, but if I represent it in the Newman projection, see the bromine is here, this is this carbon, this is the other carbon, this is this carbon. So my bromine is in the equatorial position, so it's like this, and there is a hydrogen there. Now behind it, it's this part, it's that inversed M, and you see the chlorine here is on top, and it's in the equatorial, which is, it's not up here, it's down here. So what does it tell us? You see this, both of them are at the bottom. They're pointing down. So this is a cis. This is definitely a cis. Now, if I put this structure, you have a CH3 here, and you have a Br here. Is this a cis or trans? Well, we can also represent it in the Newman projection. This bromine is now here on the right one because I'm watching this way. So the bromine is going to be on the right and this carbon will be on the other side. And I'm not interested in what it's on it because it's only hydrogen. And then on the top here, the top, there is a CH3. So again, the bromine and the CH3, they're both going down. So that's also a cis. Now, one more. So here we have a Cl, and here we have a CH3. So I can look at it from this position. So now I have an M. This has a CH3 up, and these two are here. And then behind them, they're attached to this carbon, which has a Cl right here. So you see, one is going up and the other one is going down. So this is a trans. Another one more. So here we have a CH3, H, CH3, H. So if we represent them with the inverted M on one side, it's a W and an M. So here, this one is this carbon, and it has a CH3 on top. And then in the back, this is this carbon, and it has a CH3 down here. So you see one is up, one is down, so that's also a trans. So this concludes the little introduction for conformers, and I hope you understand now what are conformers and how they are used. Conformers are the same, the representation of the same molecule, but it's caused by single rotation around the CC atom. Now, for normal alkanes, you go from the eclipse to staggered to eclipse to staggered. For the cyclohexane, you go from one ring to another. The axial becomes equatorial, and the equatorial becomes axial. And that concludes this part of the chapter, of the module, I should say. Thank you.